Welcome to Mathematical Analysis. Today we are going to explore a fascinating and highly practical mathematical tool known as Newton's divided difference. Imagine you are tracking a car's journey, but your GPS tracker is glitchy, recording positions at completely random, uneven time intervals. Standard prediction rules fail here because they rely on perfectly even gaps. How do we guess where the car was at a specific missing minute? This is exactly the problem we will solve today. Let us dive in and see how mathematics handles messy real-world data. To understand why this method is so important, we first need to talk about interpolation. Interpolation is the process of estimating an unknown value that falls between known data points. Often we are taught methods that assume our data is perfectly equally spaced. But in reality, data is messy. Newton's divided difference is a specific technique used to construct a smooth mathematical curve, a polynomial that passes exactly through a set of given points, even when the inputs are completely irregular. It does this by calculating the rate of change or slope between points, explicitly divided by the specific distance between their coordinates. Now that we understand the goal, let us look at the mathematical building blocks. We start with the zeroth divided difference, which is simply the raw output value at a given point. From there, we calculate the first divided difference. Conceptually, this is just the standard slope formula from basic algebra. The numerator represents the change in the output values, while the denominator represents the specific uneven gap between the input values. If the gap between inputs increases, the rate of change adjusts accordingly. This gives us the exact slope for that specific interval, forming the foundation for our polynomial. Building on that first formula, we now move to higher order differences. To find the second divided difference, we look at the rate of change of the rate of change. Notice that the numerator uses the first divided differences we just calculated. The denominator is crucial here. It is the difference between the x values that are 2 steps apart in the original data, spanning across 2 intervals. As we calculate third or fourth differences, this gap in the denominator continues to widen. If the outer x values are further apart, the denominator grows, scaling the difference down. This hierarchical process continues until we run out of pairs. With our differences calculated, we can finally construct our polynomial. This formula might look long, but it is built systematically. We take the top value from each column of our difference table and use them as constant coefficients. The terms with x minus x0 ensure that if we plug in one of our original data points, all the subsequent terms cancel out to 0. This brilliant algebraic trick guarantees that our curve passes exactly through every single known data point. If we increase the number of data points, we simply add more terms to the end of this equation. Before we apply this to a real problem, let us visualize how we organize these calculations. What you're seeing here is the structure of a divided difference table. On the far left, we have our raw inputs and outputs. Moving to the right, the arrows show how adjacent pairs of numbers are subtracted and divided to form the first divided differences. Those new numbers then pair up to form the second divided differences, and so on, creating a triangle shape. The most important part of this diagram is the top diagonal, which is circled. These specific numbers at the top of each column are the exact coefficients we plug into our polynomial formula. Now that we have seen the table structure, let us put this into practice with a concrete example. Suppose we have 3 data points. At x equals 1, y is 3. At x equals 3, y is 11. And at x equals 4, y is 21. We want to estimate the value of y when x equals 2. Notice the gaps between our x values are 2 and 1, so they are unequally spaced. We start by finding the first divided differences. For the first pair, we subtract the y values and divide by the difference in x, giving us 4. We repeat this exact same logic for the second and third points, which gives us a slope of 10. Continuing with our table, we now use our first divided differences, 4 and 10, to find the second divided difference. We subtract 4 from 10 in the numerator. For the denominator, we must use the total gap between the outermost x values of this group, which are 4 and 1. This gives us a second divided difference of 2. Now we have our top diagonal coefficients, 3, 4 and 2. We plug these directly into Newton's general formula. This creates a custom-built polynomial equation that perfectly fits our 3 original, unevenly spaced data points. With our custom equation ready, we can finally answer the original question. We want to find the value when x equals 2. So we simply substitute 2 for every x in our polynomial. Following the standard order of operations, we simplify the terms inside the parentheses first to avoid any arithmetic errors. This leaves us with 3 plus 4 minus 2. Adding these together, we get our final estimated value of 5. Physically, if this were our glitchy GPS tracker, we would confidently estimate that at minute 2, the car was exactly at position 5. So we have successfully interpolated a missing value. But what happens if we collect more data? One of the greatest strengths of Newton's method is how easily we can update our model. If a scientist collects a new data point from an experiment, they do not have to throw away their work and recalculate the entire curve from scratch. Instead, they simply add a new row to the bottom of their existing difference table, calculate the new diagonal entries, and tack one single new term onto the end of their existing equation. This saves massive amounts of computing power in real-world applications. Let us see this incredible efficiency in action. Suppose we discover a fourth data point for our previous problem. At x equals 6, the value is 73. We want to update our polynomial. First, we find the new first divided difference between our last known point at x equals 4 and this new point. Subtracting the values gives us 26. Next, we use this to find the new second divided difference. We take our new slope of 26, subtract the previous first difference of 10, and divide by the new gap from 3 to 6. This gives us 16 over 3. Continuing our update, we now have enough information to calculate the third divided difference. We take our brand new second difference, 16 over 3, and subtract our previous second difference, which was 2. The denominator spans all the way from our very first point at x equals 1 to our newest point at x equals 6. To simplify the numerator, we convert the whole number 2 into the fraction 6 over 3. This makes the subtraction straightforward, leaving us with 10 over 3, all divided by a total distance of 5. We are now at the final step of our update. Dividing 10 over 3 by 5 gives us 2/3. This single number is the only new coefficient we need. To update a polynomial, we do not touch any of the old terms. We simply take our previous equation and add one new term to the end. Our new coefficient, 2/3, multiplied by x minus 1, x minus 3, and x minus 4. The old curve is perfectly preserved, just slightly adjusted by this new addition to pass through the fourth point. Now that we have used this formula, let us understand how it connects to the broader world of mathematics. You might wonder how this compares to Lagrange's interpolation formula. Because there is only one unique polynomial of the lowest degree that passes through a given set of points, Newton's and Lagrange's methods produce the exact same final equation. Newton just builds it piece by piece, making it easier to update. Furthermore, if your data actually happens to be perfectly equally spaced, all the denominators in our table become constant multiples. The formula naturally simplifies, reducing exactly to the standard Newton's forward difference formula. We have covered a lot of ground today, so let us review the most important ideas. First, Newton's divided difference is an incredibly powerful tool for estimating values when your data points are scattered at uneven intervals. Second, by calculating rates of change over specific gaps, we build a hierarchy of differences that give us the exact coefficients for our polynomial.
Third, this method is highly efficient, allowing us to add new data on the fly without recalculating everything. You now understand a universal parent formula that gracefully handles messy real world data. Excellent work today.